Hello students, today we will discuss fourth numerical on friction chapter, and this is the third numerical on equilibrium of block category. In the previous two videos I have discussed two numericals which were based on equilibrium of block. So let us solve one more problem on the same category. Now let us read the question first. Determine whether the block shown is in equilibrium and find the magnitude and direction of the friction force when theta is 40 degrees and P is 400 Newton. Take coefficient of static friction as zero point 0.2 and coefficient of kinetic friction as 0.15. So we are given one situation. In this particular diagram, one block is given which is resting on an inclined surface. The angle of inclination for that inclined surface with the horizontal is 25 degrees, and the weight of the block is 800 Newton. To that block, one lever is attached, and on that lever one pull is applied. The magnitude of that pull is 400 Newton, and this particular lever or this pull is at 40 degrees to the horizontal. Now in order to solve this problem, we first have to draw the free body. So in order to draw the free body, what we will do, we will draw the angle, the inclined surface first. So we have drawn inclined surface, we have shown that inclination also 25 degrees. On that surface we will draw the block. After that we will draw this lever. So let us draw that lever. Now we will show the forces acting in this particular free body. The first force to label is the weight of the block. It is 800 Newton, sorry. So let us show the weight of the block in vertical downward direction, and let us say this is the point of application. And why we are showing this as a point of application, just to make the free body more clear, easy to understand. So let us label this weight as 800 Newton. It is acting in vertical downward direction. Then we will label the normal pressure. Normal pressure is always at 90 degrees to the inclined surface, so let us call this as N. Apart from this, these two forces, now let us label this pull, and it is given as 400 newtons in the statement, so let us label that value over here. So after this we have to think about the friction force. So in the previous videos we have learned that when we have to solve such problems, we have to make one assumption regarding the motion of the block. Right now we don't know about the motion of the block. We don't know whether the block is moving in downward direction, in upward direction, or the block is in equilibrium. So let us assume that block is moving in upward direction. So if the block is moving in upward direction, the friction force will act in downward direction. So we have assumed that block is moving in upward direction, and against that motion we will consider the direction of friction, which will be in downward direction. Let us label that friction as F. Now we have labeled all the forces acting in this particular free body. Now next thing is we have to think about the axis. So in the previous videos we have learned that along the inclined surface we will consider x-axis, and normal to the inclined surface or the perpendicular to the inclined surface we will consider y-axis. Now after that, what we need to do, we should resolve the forces into its components. If we will talk about normal pressure, it is acting along y-axis, so there is no need to resolve it. Friction force is purely acting along x-axis, there is no need to resolve friction as well. But if we will talk about the weight of the block, it is acting in downward direction, vertical downward direction, and that means it has some angle with x-axis and y-axis. It means we need to find the components of this weight first. So how to find the components? Suppose this is the point of application. From that point of application we will draw two lines. One will be along x-axis, or we can say along the inclined surface. So let us say this is the first component, and second component will be along the y-axis or normal to the inclined surface from the point of application. Now you see this particular arrowhead is acting towards the point of application. So in these two components also we will show their components, show their arrowheads towards the point of application. Now if this angle is theta, so by geometry this angle will also be theta, 25 degrees. So this will become cos component, this will become sine component. So we label this as 800 cos 25 degrees, and we will label this component as 800 sine 25 degrees. So after this, what we have to do, we have to think about this particular force. Now you see this particular force is also acting at some angle to x-axis and y-axis. It means we should draw the components of this force as well. So let us say this is the point of application for that particular force. So from that point of application, we will draw one component along x-axis, or you can say along the inclined surface, and second component we will draw along y-axis or normal to the inclined surface. Now you see arrowhead is moving away from the point of application, so in these two components also we will show away from the point of application. So now we have to consider the angle of this particular resultant with this particular component. So how to find that angle? Now you see we are given 40-degree angle for this particular force with the horizontal. It is given as 40 degrees. So we have to find this angle. So how to find this angle? So at this point of application, if I draw a horizontal line from this point of application, let me draw a horizontal line. So it means this total angle is 40 degrees. Means this particular force makes 40 degrees angle with the horizontal. So with the horizontal, 40 degrees are shown. But if you will consider this particular part, you see this particular part, so this is 25 degrees, so this angle will be 25 degrees over here. See, this is the horizontal surface, so this is the horizontal surface, this is the inclined surface having angle 25 degree with horizontal. So parallel to that inclined surface we have a vector here. It means this angle is also 25 degrees, 25 degrees, 25 degrees. So 40 degrees minus 25 degrees, we will get 15 degrees. So we got our answer that this particular force makes 15 degree angle with this particular component. It means this particular component will be 400 cos 25 degrees, sorry 15 degrees, because the angle is 15 degree, and the second component will be sine component, that is 400 sine 15 degrees. So now we are ready with the free body. Now we have to draw, we have to solve this problem. So first of all, we will use equation summation fx is equal to 0, because we are considering that this particular block is in equilibrium. So we will first find what is the frictional force required to achieve this equilibrium. So for that we have to apply summation fx is equal to 0. So how many forces are acting in x direction? First is this particular component. This component is 400 cos 15 degrees, and second is the frictional force, and third component is 800 sine 25. Now this is acting towards right, so we'll consider this as positive. This component is acting towards left, we will consider this as negative. Frictional force is acting towards right, we will consider this as positive. So our equation will become 800 sine 25 degrees plus f minus 400 cos 15 degrees equal to 0. So when you will solve this equation, you will get frictional force required to maintain the equilibrium as 48.27 newtons. Now we will use the second equation, second step, summation fy equal to 0. So how many forces are acting in y direction? 800 cos 25, it is acting in downward direction, so we'll take this as negative. Second is 400 sine 15, it is acting in upward direction, we'll take this as positive. Normal pressure acting in upward direction, we'll take this also positive. So equation will become n plus 400 sine 15 degrees minus 800 cos 25 degrees equal to 0. So from here we will get value of n as 621.51 newtons. So third step is we will find maximum frictional force for this particular situation. So how to find this? We will apply the formula Fm is equal to coefficient of static friction into normal pressure. So how much is the coefficient of static friction given to us? 0.2. So 0.20 into 621.51 calculated in the previous step. So from here we will get Fm, that is the maximum value of static friction available for this particular situation, and that is 124.30 newtons. Now in the fourth step we will compare the frictional force required to maintain the equilibrium and the maximum frictional force available for this particular situation. Now as you can see that frictional force required to maintain the equilibrium is very less as compared to the maximum frictional force available for this particular situation. It means the block is in equilibrium. So we got the first answer. Now what he's asking in the second part, find the magnitude and direction of the friction force. So if the block is in equilibrium, it means for equilibrium the friction force is 48.27. So answer for the friction force is 48.27 newtons. I hope this particular numerical is clear to you. Thank you very much.